Okay, here we go. So, where we were roughly is we were right after we had done some turning the axis off and we had just learned how to use the canny edge detector. This is roughly where we were at. We were trying to figure out how do we actually use the canny edge detector versus the logarithmic edge detector. So the method is what changes, the actual method name here. So the logarithmic. So let's take a quick look at this. Oh, I'm going to need to run this section. Okay. So I'll run this section because it has to reload everything. A couple of you are having connection issues. Awesome. So here we go. We have to do all of them again because we've got the image data. Nope, computer has slept since then. So we need to go back in, add folders and subfolders. Now it'll actually have access to the data, blah, blah, blah. So we need to run first section. This is another thing that, again, every time you start MATLAB, even if it was previously running, each sort of new session, you have to go back in and include all the folders and subfolders of whatever your project was. So, okay, we have images loaded. I imagine there will also be some questions. There have still been a couple questions regarding the other data, so we'll go over that at the very, very end as far as how to make use of that, because this one is kind of a bear of a project. All right, second section. I'm going to go ahead and run this now so it can actually pull in the data. And it'll take a little bit to actually run through and calculate what the canny edge detector is going to pick up. What that'll also do is that will help give us all of the pieces that we're going to need. So this one is already done. I'm going to go ahead and open this up in a figure window. And assuming I can actually get this to show up, it's going to be a little bit tricky to make it work while it's running. It doesn't like to do that. Once it finishes churning through the canny image processing here for edge detection, this is what I was working with one of the other classes with. We do the edge detection and then we do the resizing of that same array by selecting data out of it. You guys remember what the colon means? It's a really big, important aspect of MATLAB that my seniors had forgotten. Who remembers what the colon means in this context? Means all, correct. All is what you're looking for. This means all of that, in this case, all of Z is the colon. So we should be done in a couple seconds here because it's going through the edge detection. If you were to do something silly like if you were to unsuppress this output, it would output some very different sorts of things for each of them. So what we're going to do is these two have exactly the same settings, and we're going to look at them quickly side by side. So we have one here, and because I opened it twice, I have two copies now. So it did save the instructions. But let's take a look here at the two side by side. Here we go. The two side by side give us a very interesting comparison because we can see the canny edge detector is much more detailed in the region of interest. You can see the other logarithmic detection is not, it's not quite as smooth in most areas. So it's almost a little bit more choppy. So a lot of things that it won't pick up that we do pick up over here with the canny edge detection. So this is why this is used so often as a method. Using the same parameters, you get a lot higher resolution for roughly the same compute load. So there we go. So we've now done the Gaussian. Now, it goes through and does the isosurfacing and isopatching in order to, or the patching of the isosurface in order to get all of the information to be able to get our 3D render. So this is a representation. So this one we can take a little closer look at. What do we see as far as the actual data? What do we actually see in this? So if we rotate it, come on, catch up, catch up. We are moving slow as molasses today for reasons I can't explain. Probably Zoom's fault because Zoom consumes all that is holy. There we go. So if we rotate this just like so, we have our representation. So this is top, this is bottom. Here is our jaw. Here's our upper mandible. And then we have this thing kind of off to the side. So what does that look like? Anyone figure out what this is? This particular object? It's clearly not part of the rat. It can be a reference object or can be used as a reference object. What would be concentric circles if you're thinking in terms of 3D slices of a thing? Uniform concentric circles. What would make a shape like that? Anyone know? How about a tube? A tube taken three-dimensional slices would look almost like a stack of washers as it builds this image. So this is actually the tube that was used to bring oxygen into his little mouth. It just comes up alongside his body and then curls around into his schnoz so that he can breathe oxygen while he's sedated. So here you can see the lower jaw edges and then the upper mandible and some of the definition of the sinus cavity as well. All right, so we've got our 3D image. Great, fantastic. Then what? We come down here and we need to build a Gaussian kernel. Okay. How many of you have heard the terms Gaussian or kernel before? Raise of hands. Strange. I'm not seeing hands. Fantastic. This is why we're going over this particular project, because this is pretty rough. So we have to have a function that allows us to do this thing. So you guys probably have not had a statistics course, but somewhere, some place, you have seen an example of the curve. So as soon as I draw it, even badly, you guys will recognize it. So anyone recognize this? Should look familiar. Yeah. Okay. We've reestablished connection with reality. Professor's no longer speaking Martian, or is he? All right. Here's the mean. And we have ranges, something like this, where we have what are called standard deviations, sigma 1, sigma 2, and sigma 3. So 1, 2, and 3 standard deviations. So what that does is that contains different percentages of what we would expect to find if this is the average and something is what's called normally distributed. So normally distributed means this is the average. And then depending on how big the standard deviation is, that sets how wide or how narrow the curve is. And so there's a whole bunch of parameters for normal components here. So things to consider. This is a very valuable thing for a lot of data analytics and stuff later, but that's a 2D representation. In the context of what's happening in, for instance, our little rat over here, what is happening? Let me scroll up on this part real quick. So the little rat in the center of the chamber, I'm going to change colors. What is actually happening to the rat? This is going to be dramatized Dr. Seuss style because it entertains me. What's happening to the rat? They're in a CT scan. So there's a specific kind of radiation being used. It's technically MRI is missing a letter. It's actually NMRI. It's nuclear magnetic resonance imaging. Engineers thought that sounded cool, and then the people got a hold of it for medical uses, and they were like, no, you can't include the word nuclear in a name of a medical device because it's never going to fly. So it is a high radiation source, and so we get gazak, 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 right? We get Mr. Brown going gazak, gazak, gazak all over the place. And what's happening in the center as all of those fields converge in the center? We get a higher concentration. So we get a higher concentration toward the center, and that means we get lots more data samples here at the center than we do elsewhere, right? So what we have to do mathematically is take that into account and take this, and let me change colors again here. We have to spin this around and revolve it in 3D so that we get a three-dimensional example of what this looks like. And so when we do that, what we're going to see, let's see if I can get it to line up here. What we'll see is as we focus this, it will, I almost bullseyed it, not quite, but pretty close. It will overlap with our central area in this image. And what we're going to do is we're going to create this effect, and then we're going to do a couple other things. Now I will go through and explain what we're doing in this part, but won't necessarily make complete sense to all of you. So we'll try and make it make as much sense as it can, given the sum total of things we know at this point in time. So here we go. We have to build the Gaussian kernel to give us this starting point, this image. Okay. Knowing that, we come over here to that Gaussian kernel thing. You guys wondered what this had to do with life on this planet. Well, you're about to find out. So we have a couple things, and because you guys haven't had a statistics course, this won't necessarily make tons of sense. But what this is saying is this is actually X bar, the average of X or mean of X minus X naught. So X at some point, the difference between the two of those squared, meaning it doesn't matter technically which order you do them in, because it's the difference between them and the square of that. So it by default takes the absolute value of those. This is essentially what's called an RMS of error. This is taking a at the end, effectively canceling out a square root to get a root mean square of a difference between the average and a single individual point. So it will calculate some of the differences. And we're going to need this in order to get to some of the next steps on this particular project. So if you haven't opened up your Red Bull yet, you're probably going to want to start right about now. So first thing we know we're going to need is we're going to need to do stuff with our inputs. We have two inputs. We have size and sigma. Well, we know what to do with the sigma. Based on the formula here, what do we need to do to our sigma? Bueller. Anyone? What do we need to do with our sigma? Based on our formula, this is our Greek letter sigma. For those of you that haven't learned Greek extensively, exactly, we have to square it. So we need sigma 2 is equal to sigma squared. So we're going to suppress output for those. Now, there's another piece of this that's not necessarily going to make all the sense in the world, and we'll come to learn why exactly. This is a thing that simply won't make tons of sense until we get there. So we need to put this whole entire equation in. So we're going to say H, because that's our output, H equals, and then we need to put that whole expression into place. So we have to multiply that first coefficient times, and then we have E. How do you think we represent E in MATLAB? Do you guys remember from the training? How do we represent E? Good. EXP. Now in live scripts, they really go out of their way to help make sure you can do stuff. All right. So EXP, we're going to need a couple of these, because the first one needs to be our numerator. I'm going to do a little bit of cheating here, and I'm going to use the numerator as an addition of just two squared terms. So this will save me a little headache and heartburn later. So 2 times sigma 2. So that's our 2 sigma squared in the bottom. And now we have x squared, and we're adding to that based on our formula, capital Y squared. Now, because these are going to be, because these are arrays and we're working with matrix and things that we're going to generate, because keen-eyed among you will notice we don't have any X and Y, and that doesn't come from sigma. We'll get there. I'll explain this, but it may or may not actually make a whole lot of sense. So the X squared, because of the way that we have to do this, it's element-wise squaring. So we have to do element-wise squaring in order to get these to calculate correctly. That's because you're not able to multiply a vector by itself because of the way that matrix math works. So if you need the values of the individual numbers squared, you have to go through and do element wise instead. So that goes through and squares element by element which gives you actually x squared instead of just typing x squared, which would give you x times x transpose kind of thing, and that just doesn't work exactly. While theoretically that should give you the same sort of result, it will actually not. And you'll learn more when you get to linear algebra as far as why that is. But we don't have time to teach you 12 different classes all today. So this has to include our first coefficient, 1 over, actually I can put the 1 outside, make life a little easier, because of order of operations. Anyone remember the acronym for order of operations? You sure ought to. Type it in the chat if you remember it. 2 times pi times sigma 2. So that's our sigma squared. Yeah, PIMDIS, good. Okay, a few of you remember the important things you learned in school. All right, so here's a few of the other things that you'll need to include. One of them is we want to include this piece of it. We want to include our x and y. The question is, where do those come from? But before we can answer those questions, we of course have to ask another question. And when we ask questions, we go to the MATLAB help, because the MATLAB help knows all. So the new $12.50 word you're learning today is mesh grid. What we're going to do is create a mesh grid. Well, this is our syntax for a mesh grid. Actually, this one is our syntax for the mesh grid because it's going to be a square mesh grid. We're going to copy this over and we're going to take a closer look at how this operates. So our mesh grid, but it's not going to be of X, it's actually going to be of size, our input. Then we're going to suppress this. This is where our X and Y are coming from. Okay, you've lost me. I have no idea what you're doing. Good, I'll explain it and then it still won't really make sense. So this is creating a two-dimensional grid with X and Y coordinates that counts up by, in their case, they've defined these values for X and Y. I've just defined that the mesh grid is going to be of a specific size, which is the second case here. This one, a mesh grid of X, which is some range. So some range from -2 to 2. So -2 to 2, they created a mesh grid onto which they plotted a surface. So think of this as like a digital workbench or a digital picnic blanket that you can form in 3 dimensions to work and show the behavior of a system with multiple simultaneous variables. In our case, we're trying to take that thing where we did the bell curve, the normal distribution, and rotate it 360 degrees. And we're basically going to impose that upon the mesh grid so that we get a 3-dimensional representation of the mesh grid. All right, so that's what it is that we're doing. But in order to use those data points and actually compose our mesh grid and form it in 3D in this way, we have to do a little more math here and figure out the difference between the mean and that range X. So X at any given point. So what that means is we need to use the mean formula, and there's something we need to understand about the mean formula, because we're going to put down a formula. X, capital X, is equal to the same capital X, except we want it to be our whole equation here, which is x bar minus x naught. So the mean of x minus x. Now, the mean of x is going to take the whole range and get an average, and x is going to be at any specific different point. That difference between those, that whole range squared, is what's going to go into our exponential here. All right, we're going to do the same thing for y, and we'll take a look at what exactly that's going to do, because we need to look at one more thing with the mean before we really understand how this is going to operate. So we're going to do the same thing for y. All right. So mean is something we need some information about. So what do? We go to the help, because unlike in Arduino, where you guys have used mean in the past, this will be a little bit different, because a mean is not a mean is not a mean because of this. The mean of just an array of numbers will give you the mean. But when you put in the mean of A, what you're going to get is you're going to get three different means. So this is the mean of the first one, the first column, that is, the mean of the second column, and the mean of the third column. Well, what if you just wanted one number? If you're looking for one number of the mean, you can't just take the mean of a matrix, because that doesn't do the thing that you think it does. So then you can take the mean of the rows, and you'll get the mean of the first row and the second row and the third row and the fourth row. So in order to get back the average values across that whole range, you have to get the mean for x across the rows instead of across the columns. So the y's are going to have to be across the columns, and that's what it's meaning. So the y has to be along the rows, meaning the first kind of mean. So we'll show you one example where we do the first column, and if we just leave this as comma 1, which is effectively the default, we're going to look at this first and see what this actually means in terms of the output, because I'm not sure it's going to make any sense whatsoever until we look at the output. So right now this is incorrect, and we'll see why, because we should get a picture like this. Because remember, we're revolving the bell curve thing, right? Seems pretty straightforward. We have a function that we've just defined, and we need to call it. So how do we call the function? This part you guys should know. What does it look like to call our function? H is G kernel, so that's the name of our function. So we don't have to try and write this into the code down below or any crazy nonsense like that. G kernel, because we've defined this, it knows we need size and then sigma. So this one, we're doing a 20 by 20 with a standard deviation of 3. So the sigma is going to be 3. Our size is going to be 20. Now, there's some other sort of error handling that you can build into the G kernel if someone forgets to do two inputs and other things. I'm not taking you all the way to understanding that full level of logic yet, because I want you guys to sort of kind of understand some parts of what you're doing. We're going to use image SC, and we're going to display it. So what are we going to put into image SC? What do you guys think? What are we going to plot using image SC? There we go. Somebody got it. H. Because H is the array that we've just calculated using the G kernel, doing all of the things so that we can make the mesh grid, so that we can turn the mesh grid into a three-dimensional function, UC. So what this will do, let me run this section, is this will plot. Now you notice that we get something that doesn't look anything like that, right? So here we need, I wonder if it's just the mean of this one. I want to make a quick change here. I'm going to let it try and do the default mean. Let me rerun that real quick. If we do the default, just the normal mean, and I rerun this section, nope, I've still got to trick it. All right, so the difference between the mean and this is which direction, which dimension we're taking. So if we do the mean for this one in one direction and this one in the other direction, what we can get out of that is we can get, now you're not giving me the correct value here. This needs to be updating. This needs to be updating using the mean of these two. So sigma squared, that one's fine. Our mesh grid definition is fine. We've got our means correctly connected. Let me just double check that I didn't miss one of my values here. So sigma 2, we've got our 2 sigma squared, that part's correct. And our x squared and our y squared. All right, so those two are actually set up correctly. So this, let me run close. Let me run close that window. I wonder if I can close that one independently. I don't think so, because that's just the, if I clear that output and rerun it. Nope, it is not updating correctly. All right, so this has one more piece. We've got the correct calculation going on, and H should be storing correctly. This is still calculating correctly as a function. You don't have to encapsulate this first part separately, because it doesn't really change order of operations. But that coefficient should be multiplying by the 1 over the exponent. So just in case it's getting confused about order of operations there, I'm going to rerun this section. That should give me, what I'm trying to get it to show you is the error band because this is not outputting correctly at all. So it needs to be 20 is correct because, hold on, this is, the mesh grid has to be size by size. A whole bunch of reasons why this has to be size by size, because it's giving you a single column or a single row array is what it was outputting there mathematically. And that's what's incorrect. So now let me go back and fix the intentional mess up to show you what I was actually showing you a second ago. So I'm going to save this, switch back over, run this section. And now, nope, you need to be showing this calculation correctly. Mesh grid is correct, size by size, and mean of X. This one will have to be second direction. This one will have to be first direction. So let me see, why is this outputting? H is not a single value. It's calculating the output for H as a single value. It doesn't have to be looped. The mesh grid has to run first in order to get the X and Y values put together in the array. But everything that happens internal to this function gives a value. So we're not using a sum. So H should be being output as an array. So that part should be correct. All right, so let me get you started on this next section, and I will spend a minute or two troubleshooting that, because this is an important aspect. What we're going to need to do is we're going to need to create what's called a blurry image. We're going to call it B image, and it's going to be the same. It's going to be the same idea. It's going to be called the same. But I'm going to get you guys started on that for just a second, and then so I'll set up breakout rooms for just a couple minutes here, and I will go back in and figure out why the correctly sized mesh grid is coming out as a single point value where I should have a range that is being output. So I got it element wise calculating, which is all correct. But I have to figure out why it's still fighting me on that point. So go ahead and get a start on trying to put down some of the code for same thing. You're going to display your particular image at the end. So it's going to be using image SC, just like we did above. We're still calling the same Kernel command. And that should be functioning correctly here in just a second or two. So I'll pause here, get breakout rooms open, and that will make things a little. All right, so I think we've got most everyone back. So we're going to talk about what is wrong with that version of the kernel code. The mesh grid has to run and be set up as the 1-to size of the array because reasons. So 1 to size, in both directions. It's not just as simple as size in both directions, because it needs to know that you're feeding it an entire array of data, and that's how it creates this mesh grid. So it goes from 1 to size at the other corner. And that means in this case, whatever size we need to make this, it can accommodate it, which is helpful. So this allows us to generalize it to the later aspects. Now I've left the directionality off of these in order to run this to show you what I was trying to show you a couple minutes ago. And that is this. So what you see is it has a gradient in Y, but not in X. It's exactly the same number in X. So this does not represent the plot that we want. What this is essentially taking something like the bell curve, and it's a bell curve in Y. So it comes up and comes down in Y, and then stays the same all the way across in X. And that's not what we want, because right now this is calculating the mean fundamentally in the wrong direction. So this fixes the code and establishing the default mean makes the code proper for Y, so that now in this case, and I think maybe a better demonstration would be if we were to show it this way, for instance, and do it improperly on purpose the other direction, what you would see is the other direction. So now it's distributed in X, but uniform in Y. That's not what we want, because that's not what is most closely representative of the physics involved. So we need the default for Y. We need to take the X average along columns for the X's, and then the Y averages along the rows for the Y's. And that's what allows us to actually get our circular profile, which is what we're after. Then we can increase the standard deviation. We increased it to 5, and we reran that section. We increase it. We can increase it to 10. We can see how this would change. So we now have control over correctly calculating Kernel command, and now we can take that and apply it to the next step. So now we need a 40 by 40 in order to do a thing. And this is a term that you guys haven't necessarily seen before, or you've heard things being convoluted. Some of you are like, is that like the steel that they put on buildings? No, that's corrugation. It's a totally different term altogether. Convolution is a thing that we also are going to need to look up some information on. So once we've created a mesh grid and done a thing like this, a lot of times we're going to have to do what's called a convolution, and we're going to do, in this case, convolution in 2D. So we're going to use the conv2 command. And typically what that means is we're going to take something like that mesh grid, and then we're going to convolve two data sets to it. And what that means is you're going to combine the data sets from one function and apply that to the surface formed by this mesh grid. And what the convolution does is allows you to superimpose the behavior of one function on the plane of another function. And so this is a thing that's done a lot in electrical engineering for signal processing and stuff, and things that you guys will learn a lot more about later. For now, think of it as we're putting the blur, in this case, it does look something roughly like this. We're putting the blur onto the image of what we are doing. So we're going to create, by doing this, by convolving these two things, we're going to put the Gaussian, we're going to put the Gaussian together with the image above this one to make a blurry version of the image. Are you following? We'll see why. It won't necessarily make sense why exactly we have to do that, but we need to do that. So how do we create B image? That's one of the next tricks, is how do we create this B image? First, we need a normal image to compare. So we'll call that something like normal image. That's going to be equal to, just like what we've had above, out of our data set IMG, we're going to say we're going to need an image, and we're going to say all, and those need to be commas, all. Unfortunately, not all, and Fred. Fred is used elsewhere. We're going to do all, and 1 for our normal image. And then what we can do is we can take our same H. We're going to generate that H from our G kernel, because that's what the prompt is asking us to do. We're going to generate the H from the G kernel. And what we're going to do is we're going to run a 40 by 40, and we're going to run a standard deviation of 10. So that's what we're told here. So we need a standard deviation of 10. So that's going to calculate our H. Then we're going to do an image display, because we need to see what that image actually looks like, but we need to make the image first. So we need to take the normal image and the image from H, and we need to superimpose those on each other, called convolving. So this is what that B image is going to be. So B image is going to be the convolution. So convolve to of, and then we put our two matrices. So we're going to convolve our N image with our H, and we're going to use the option of same. The mechanics of why we're choosing that, don't ask questions you don't want the answer to. And then we're going to display that image using the image SC. The image SC is going to be of the image. So we have B image, and then we can set our other parameters. We can set our other parameters up here. B image, and we can do our color map, and we'll do gray. Then we're going to do our we're going to specify for a lot of the images so that we get these kinds of cleaner, crisper images at the end. We're going to specify our visibility as off. Image is the object or the object type that we're dealing with, the style, and then off. So when we run this, what we get is this thing. So it's an awful lot of work to make an ugly picture. So fantastic. We made a blurry image. So now what are we going to do with it? Well, so you know how in Star Trek, when they press buttons and they just issue commands like enhance, 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 right? And so they start with a 720 image, and then they zoom in and they somehow get an 8K still image with 100x zoom, right? That's not actually a real thing because the data is just not there. However, you can do some things like this, and you can apply a Gaussian blur. And then what we're going to do is, now that we have a blurry image, we're of course going to subtract that from the normal image so that we take the blur out of the image that we just created from the image. It makes perfect sense. Trust me. So in order to do that, we have to subtract the pixel values from the blurred image from the pixel values in the unblurred image. And that way we'll be left with just the sharper image. The sharpened image is what we're creating here. So anyone want to hazard a guess as to how we subtract one image from the other? This one's pretty scary and complicated. Any ideas? How are we going to create that? We know we're going to call it MSK. Okay, so that was the easy part. MSK is something. And then we need to do image SC of MSK. Okay, so we'll display this and we'll do the same things. Color map, etc. Because we do those in order to make them look more like the images we should see. And then we also want to see what? We have to do the actual math behind it. So yeah, someone had the audacious recommendation of simply subtracting. So we do normal image minus, because they're just arrays of data, right? They're just number of pixels with an intensity value stored in them, essentially, more or less. So n image minus the b image we just created. So we subtract the two, and that's what's called our mask. And now the mask is what we're going to use to do the things that we're doing here. The color map, axis off, all the things. So now when we run this section, what we get is this. So this is going to be all grayscale. So let's take a closer look. So now we can see where the Gaussian blur happens, but we're able to take a lot of the blurriness out of the image, and you can clearly see the overlap lines of where this capsule that the rat sits in meets up. And so you can also see where some of the wire leads and things are. And if you look down here, you see these little pointy things. Any ideas what these are? Little tiny pointy things. What have we managed to find in the image that we didn't know was there? By taking away the blurriness from the image. Anyone tell what those are? Think simply. Claws. Those are his little tiny claws, or the ends of his little tiny claws, two of them. So we managed to find a thing in the image that we didn't realize was there before, because we were able to sharpen up the image. Because up here, we didn't really, like, they were present, but we didn't really know we were looking for them. Now they've been highlighted. And now we need to do the very last step of putting together the sharpened image to make everything crisp and clear. So this is the step that we need to get to in order to actually complete this and have it up and running. So in this case, we're going to do some weighting value for the mask and the image itself. So this equation is going to be super duper confusing. So we'll say this is equivalent to our weight. So W times the mask, and we add to that the image. So we add to that the normal image. So we need to define what W is in order to make this work. So we'll set W equal to 2 for now, just to say this is, we're gonna weight the mask heavier than the normal image. And then we're going to say, because of how this will work, if you try and lay multiple images on top of each other, you're going to end up with a complete saturation in the middle. So what you have to do is you have to do this process whereby you divide the masked image by the maximum value for that image in order to display that. And so this will be done using imshow similarly to image SC. So we'll do imshow of loomc, but we have to finish calculating that first. So imshow, this is going to be reassigned as the value divided by the max, and that's what we have to work through. And loomc divided by, strangely, this function, the max. So we find the maximum elements in an array, the maximum of loomc in all the data set. So this is what allows us to actually get the calculation that we're looking for. So in order to maintain order of operations and make sure there's not extra confusion, I'm going to go ahead and encase that denominator in parentheses. There shouldn't be an issue with order of operations, but that's just a small safety net. So for the image, we're going to do the same things that we did for the other things. And it's going to be a gray color map. And we're going to turn the axes off so that it looks a little sharper. So what we should see is something like this. Only I'm going to make it a little more interesting and go turbo, because turbo is always better. So now we see our sharpened image looks like this. And we see some of our focal points. We see the little claws down there. We see our breathing tube pretty clearly. And we can see parts of the jaw, his teeth, and where it's red is where it's reading some of the highest density of material. So that's how we can get crystal clear info out of our image processing methodology. So now that you guys have all been thoroughly confused into our trek about Martian operations, what questions do you guys have? So we have a whole bunch of things that we've covered, a whole bunch of new and different functions. We've learned how to use them and how to look at what we're using the help. So what questions do you guys have? Any other specific questions? So that final photo, the whole objective is that sharpened image compared to the original image. That's the process that we went through to create a sharpened version of an image. So it uses a lot of different math and a lot of different functions all at the same time. So it's a lot of new functions, a lot of things that you guys have never used before. It's a good example of how many functions there are out there. But it's also a thing that we have to keep in mind that there's going to be a lot of questions and problem areas for these kinds of assignments as we get a little bit farther in the end of the semester. So a lot of the final difficult ones are problematic. So if you're having other variable issues, like the resize image, what you need to do is you need to recreate or you need to rename the variable, because what we used instead was one that made a little bit more sense, because we went from edge image to resize, which is RSZ edge image. So we changed from edge image, or we went from edge image up above to resize edge image down below. So this is why we've made some changes to some of the variable names to make them make more sense. Other questions? All right. Well, if there's no other questions, then that's, unless you have questions on some of the other assignments, that's the extent of today's lesson. So that should be helpful for